What if you could see all the light in the universe? Not just the stars twinkling above you on a clear night, or the faint glow of the Milky Way, but every single photon, every ripple in the electromagnetic field flying through space right now, from every corner of everything. Let's start close to home. On a good night, away from city lights, you might spot around 2,000 stars with the naked eye. That's it. The sky feels mostly empty, vast, and dark. But zoom out a little. Our galaxy alone has about 200 billion stars. Why aren't they all blazing up there, turning the night into day? Distance. Each star's light spreads out in a sphere as it travels, getting dimmer and dimmer. By the time it reaches us from across the galaxy, tens of thousands of light years away, it's a whisper. Okay, but what about beyond the Milky Way? There are roughly 2 trillion galaxies in the observable universe, each packed with hundreds of billions of stars. If you could somehow collect all that light, unfiltered, undimmed by distance, it would be still pretty dark. Why? Because the universe isn't infinitely old. Light takes time to travel. The farthest galaxies we see are 13.4 billion light years away, give or take. There's a horizon to our vision, a cosmic event horizon. No light from beyond it has had time to reach us since the Big Bang. This is why the night sky isn't a wall of fire like in Olber's paradox. If the universe were static and infinite, every line of sight would end on a star, and the sky would burn at the surface temperature of stars, about 5,000 degrees Kelvin. Blinding. But let's say you could see it all anyway. Ignore the horizon. Stack up every galaxy's light as if it were right next door. The total visible starlight from the entire observable universe adds up to about the brightness of 1/60th of the full moon. Spread across the whole sky, it's faint, like a dim glow you'd barely notice. Astronomers call this the extragalactic background light, or EBL, and they've measured it indirectly. Telescopes like New Horizons have confirmed it's there, but it's drowned out by our own galaxy's dust and airglow. Now escalate. All the light doesn't mean just visible wavelengths. Your eyes only catch a sliver, 400 to 700 nanometers, a razor-thin slice of the electromagnetic spectrum. What if you could see the rest? Radio waves from distant pulsars and galaxy clusters. Suddenly, the sky crackles with invisible broadcasts, like tuning into a trillion cosmic radio stations at once. Infrared from dusty star-forming nebulae, and the heat of planets everywhere. Our own solar system would light up like a Christmas tree. Jupiter's glow, the zodiacal dust reflecting sunlight. Ultraviolet from hot young stars. X-rays screaming from black hole accretion disks. Neutron star collisions. Gamma rays from supernovae and the hearts of quasars. If your brain could interpret all that as visible, the sky wouldn't just brighten, it would explode into chaos. Overlapping spectra, colors beyond imagination, pulsing, flickering, shifting as sources move relative to us via Doppler. The cosmic microwave background, that faint echo of the Big Bang filling space evenly, would wash everything in a uniform reddish glow if redshifted into view. About 2.7 Kelvin. Cooler than absolute zero feels on your tongue. But everywhere. How bright, really? Let's perspective it. The CMB alone carries about